Hey guys, I am Gautam and welcome to Gaming. So today's video will be specially about the valence bond theory, VBT. So till now we have read about the electrostatic theory, we have read about the EAN, effective atomic number, or 18 electron rule, and now it's time to know about valence bond theory. So we are valence bond theory. So we are reading what we are learning. We are learning the bonding in metal complexes. So if we want to learn about the bonding in metal complexes, what I need to do, I just need to learn a lot of theories. So that's how we have learned about the electrostatic theory that got failed, then EAN, that little bit correct, then coming to VBT, it's also correct, more or less it's also correct, and then we will move forward and learn the CFT, then different other theories like MOT, LFT, different other theories. Okay, so this will be the special topic on valence bond theory. So without further time wasting, let's get started and put your earphone in your ear. Okay, don't get distracted. So whatever, let's talk about this valence bond theory. And before I start, I just want to tell you that why the name is valence bond theory. So you are getting some flavor from here, that here it is valence bond theory. So what does that mean? Why the valence? You know that during bonding, you know about the bonding. Okay, during bonding, which orbital or which orbit generally takes part in bonding? You know, only the valence bond, only the valence orbital, or valence in terms of old theory, only the valence orbit. You know that. Or if I from modern theory, only the valence orbital. But if you know that that the valence orbital is taking part to form a bond, and there is something like the same thing in the valence bond theory, that's why the name is valence bond theory. So yes, there is something like that. So to know about the valence bond, okay, valence bond theory, we just need to learn about the system which are taking part into bonding through valence bond theory. Or can I ask a question like that? Can valence bond theory, VBT, explain the bonding of metal complexes? So here what we are discussing the metal complexes. That means what happens with a metal, there is a ligand. With a metal, there is a ligand is connected through a CCB. What is CCB? Coordinate covalent bond. And this ligand is donating its electron to metal through coordinate covalent bond, and we will consider during this discussion the valence bond theory, we will consider the metal, because ligand can be anything. What we are learning about d block elements. Okay, and in d block elements, what are there? Those all are metal. Okay, those all are metal, and those metal are what? Those metals are especially our iron 2+, cobalt 2+, cobalt 3+, iron 3+, nickel 2+, palladium 2+, platinum 2+, palladium 4+, platinum 4+, etc. A lot of d block elements are there, and in that d block elements, or in case of those transition elements, the system, the metal are those, and those metal, as both are d block elements, so their valence orbitals are what? Valence orbitals are d orbitals, as they are d block elements, right? So these valence orbitals, like d orbitals, will take part into bonding, and as this is a valence bond orbital, so we think that valence bond theory could explain the total bonding in metal complexes. Okay, so we don't want to do anything with the ligand. Ligand can be anything. It will be a cation, it will be an anion, it will be a neutral ligand with lone pair, with electron pair, but it will come to bind with metal. But whatever business we will do only with the metal, not with the ligand. Ligand can be anything. Clear? And thus these metal will have this d orbital, d valence orbital. So whatever the d valence orbital will be, so that will decide that whether the metal will form a complex, or whether the metal complexes will be stable or not, or whether the other properties which are shown by that corresponding metal complexes are correct or not. We want to explain all of these things through valence bond theory. Clear? So without further time wasting, let's get started, and we will start this by learning a new thing. You know about that, but I can assure you that you will get to learn something new over here. I know that you know this one, whatever I am going to tell, that is, I will be talking about some orbital. What are orbitals? You know, this is s orbital. I'm not wasting my time on this s orbital. And how is it? It is a spherical. It's like a football, not a circle, not a two-dimensional object. It's a spherical, three-dimensional system. S orbital. You know about p orbital. How many p orbital are there? Px, py, pz. These three are there, right? So how these are looking like? Okay, let me draw. So take it as x, take it as y, and take it as z. So let me show you. If this is x, this is x, this is x, okay, this is y, sorry, z, and this is y. You can see, okay, my fingers are x, Apple pencil is y, this is z. So that's how it works, x, y, and z. When you consider px, it will be like that, very simple. You know all this, but I told you that I will teach you something new, and this is dz. Okay, you know, you knew this, all this. Okay, those you are familiar with this kind of system. Now let me come to the d orbital. Let me come to the d orbital. And you know how many d orbitals are there? dxy, dyz, dzx, d x square minus y square, d z square minus x square plus d z square minus y square. So there should be one. How many? 1, 2, 3, 4, 5, 6. 6 d orbital. Is it true? Is it true? Yes or no? No. You know about this. You know about this, but you don't know about this. You don't know about these two orbitals. You know what? You know that with except this one, you just had the knowledge that we had a dz square orbital. Okay, but you didn't know about this. Actually, z square orbital is what you know. Z square orbital is the combination of these two orbital that I have written over here. These two orbital. Z square orbital is nothing but the combination of these two orbitals. So did you ever think that you are getting x, y, y, z, z, x, then you are getting x square minus y square, so you should get like z square minus x square or z square minus y square, like that? Did you ever think about that? I think you didn't think, but yeah, that is important because these two orbital forms to this z square dz square orbital. The question is arising how. So before I'm going into that, I am just let me make you understand these four orbital first, because it's very important to visualize these four orbital first, then you can easily get that one. Okay, so the first one will be dx square minus y square. Okay, first one will be dx square minus y square. So this is x, this is y, this is z. So I am trying to copy this one, and I don't want to draw. I don't want to draw every time. Okay, it's done. It's also done. Okay, no problem. We are done. So now what will happen in case of dxy? So you know that in case of dxy, you have to consider only xy plane. So take it, let me take one thing, what should I take? Let me take, this two. This is x, take this black pen x, take this Apple pencil y. So if you want to have, you need to consider only this plane, xy plane, okay, not the z axis. This is z axis, you don't need to consider that. And if I show you, and if we consider dxy orbital, the orbital will be like this. From here there will be one lobe in between this x and y axis. Here opposite direction, here opposite direction. Okay, so how does it look like? It will be looking like this, xy, and this one xy. Okay, in between x and y axis on the xy plane. Similarly, if I consider dyz, same is true for this. We have to consider only yz orbital, so y and z, like this and like this. Okay, similarly if I consider dzx, we have to consider the same. Z will be like this. That means, listen here, it's not going through the y. Okay, y is like that, and to show that it looks like that it is going through the y, but actually it doesn't. Okay, it doesn't going through the y, so don't worry about that. Okay, so here it is zx, and the second will be this. So these three are dxy, yz and zx. Now let me come to the dx square minus y square that we knew, dx square minus y square. So in this case what happens, generally the orbitals are going through this x axis in case of x square minus y square, and it will be going on the from the y axis. Okay, so x square minus y square is like this. If I consider y square minus z square and d z square minus x square, so this will be like that. But remember one thing, x square minus y square, just try to understand what I am talking about. X square minus y square minus z square, and finally z square minus x square. But here it is not y square minus z square, just don't get confused over here. It's opposite one, it's z square minus y square. Okay, z square minus y square. Why is that? Just you need to do the quantum calculation, so this is not our business. Okay, this is not our business. So it will be like that. So if I just think that it is opposite, not y square minus z square, it's just z square minus y square. So now what I need to do, I need to draw this. So if in case of z and y, I just need to go through z and y, it's done. In case of z and x, I need to go through z and x, it's fine. So now you can imagine that yeah, this is our z, this is our y, and this is our x. Okay, this is our z, this is z, this is z, this is y, this is y, this is y, and this is x. So in both cases, you can see in these cases and these cases. Okay, what happens generally in the both cases, you can see that in those cases z is common. In both of these examples, both of these orbitals, z is present. The lobe is present on the z axis, and sometimes it is on the y axis, and in this case it is on the x axis. That means the electronic distribution in both the cases is through z axis one, because in both of these cases z axis is present, a lot of electrons will be present. If I add these two, then what we get? If I add these two, I told you we have to do summation. If I add these two, what we get? We will get that in the z axis we will get a lot of electronic contribution, because from first one we are getting z, second one we are getting z. So z when it gets closer, then it will give you the big lobe like that. Okay, just you can think like that. This is z square, or this is z. Okay, this is okay, this is okay. Let me again try it. Okay, this is z. Okay, and this is x, and finally this is y, x, y, and z. Clear? So in this case what happens, just look at this system carefully. In this system z is common, that's why I have written z like this, and along with that in the x and y plane, this is for x plane, x axis, this is y axis. That means the xy plane, x axis and y axis, that means in the xy plane electrons are present. Electrons are spreading throughout the xy plane from x axis and y axis. So if on the xy plane electron is present on x axis, on y axis, so you can say electron is spreading throughout the xy plane. That's why you can show like this. That what does it mean? The xy plane, this is z axis, and the lobe is like that, and in the xy plane you are telling that yeah, electrons are revolving here, or electrons are present here, electron cloud is present here. So you are summarizing the cloud like this way, and this is a donut side structure. Okay, you know that dz square is like this. So actually dz square is not dz square, dz square is we are getting dz square by the summation of these two, dz square minus y square and dz square minus x square. I think you didn't know that. And actually dz square is not actually dz square. What is that? Dz square is actually summation of these two, so that will be d, that would be d 2z square, do the summation, minus x square minus y square. Dz square is actually this. Clear? So that is what we wanted to know about that system, about the systems. So now we can enter into the valence bond theory. So let me enter into the VBT. So the basic assumption to form a VBT is that In case of VBT, what we are going to explain? We are going to explain the bonding in coordination complexes. So during doing the explanation, what I need to do, I just need to get some knowledge about the metal complexes. Okay, so here it is metal, here it is ligand. So ligand is donating ligand to the metal. So you know this bond is CCB, coordinate covalent bond, and the characteristics of this bond is sigma bond. Okay, and if I consider VBT, in this VBT there is one factor. That is about hybridization. VBT is nothing but the calculation of hybridization. Okay, if you get the hybridization, you will get everything about VBT or about the complexes. So hybridization, and you know that from organic chemistry concept or from anywhere, just if you don't know, just remember only sigma bond participates in hybridization. Pi bond doesn't participate into hybridization. Only sigma bond participate into hybridization. That's why this sigma bond, that means metal to ligand sigma bond, is very important. So you have to look at the bond, that is it is purely sigma bond or it is the combination of sigma and pi bond. So to be a sigma bond, so when a bond is forming, there will be one sigma bond, of course. If multiple bond is present, you know that the first one is sigma bond, left are the pi bond. So you just have to consider one bond if in case of multiple bonds. Okay, just one bond is sigma, but left towards pi bond. Okay, so that's why you just have to consider only sigma bond for the hybridization. And I told you hybridization is a concept of VBT. VBT is nothing but the hybridization. So that means in some way sigma bond is connected to VBT. So we need to find this kind of sigma bond in metal complexes to explain VBT. Clear? So how to find the sigma bond in metal complexes? Sigma bond will form when ligand to metal electron donation is possible. So how to do that? So we will do that for three cases: some octahedral system, square planar system, and finally tetrahedral system. So we will learn one by one each of them. So let me consider first octahedral system. We will be discussing the octahedral system first. So if we are discussing octahedral system first, so we have already discussed the orbital, how the orbitals are looking like. So now if I consider an octahedral complex, how does it look like? There is a metal over here, there is 4 ligand like this, you know that, and here also 4 ligand, and along with this you will get the 4 ligands are on the same plane, above ligand, below ligand. You know this is the structure of an octahedral system. So there are different ligands are present over here. Okay, there are even different ligands present over here, and in this case you have to consider this axis as y-axis. Consider this one as y-axis. You can consider this x-axis and the opposite one is y-axis. So for my simplicity, I am considering one this is x-axis, this is y-axis, x, y, and that will be of course z-axis. Okay, so that will be of course z-axis. So again, from orbital concept, you know that these are the different or possible orbitals. Okay, different possible orbitals, all these are. So just tell me, if this is the x-axis and in these x-axis, on these x-axis ligand is present, so which orbital of metal, which d orbital of metal directly interacts with the ligand? Because what I told you, to form a sigma bond that is related to hybridization and which is related to VBT, so a sigma bond will form when direct interaction, direct metal ligand interaction will occur. So if I find an interaction, then metal to ligand, there should be a touch like system. Metal should touch the ligand, metal orbital should touch the ligand, right? So tell me which metal orbital directly touch the ligand. Tell me one thing. This kind of orbital, if I draw this kind of orbital, this, and first let me stay on the plane. I am not considering this L and this L now right now. So this is which orbital? AM on the axis. Which one? This one, dx square minus y square, right? So we need to take that dx square minus y square. So we have got one. Another is z-axis. So you know that this will be of course dz square. This one, the last one. Okay, which is considered as a z-axis lobe. So when which metal orbital is directly interacting with these two ligands, that will be our dz square. So dx square minus y square and dz square are the orbitals of metal which are directly interacting with the ligands in octahedral complex. Clear? So that means these orbital will participate, these orbital will participate in hybridization, we can say, or these orbital interaction with ligand will form sigma bond, or we know that sigma bond participates in hybridization. So all are fine, all are going perfect. Clear? Maja aa raha hai na? Are you getting fun? Okay, no problem. Listen another thing. Okay, so octahedral system looks like this. So now, so if I am telling you that now I will consider only octahedral system, then I will come to square planar and tetrahedral system. Okay, so in these octahedral system we are going to take some examples, but before doing that, what I want to do that these orbitals, that means dx square minus y square and dz square, we have seen that these two orbitals only taking part in hybridization, that means in sigma bonding, that means metal ligand interaction, metal ligand sigma interaction. Okay, so the other orbitals, for this case, for other orbitals, the left orbitals, for example dxy, dz yz, dzx, will these orbital never this orbital should never interact with metal ligand? This metal orbital should never interact with ligand orbital. Are you thinking that? Actually no, these sometimes this ligand may participate in pi bonding, some pi bonding, not pi interaction, pi bonding or pi interaction, but those are rare. And in case of VBT or in case of hybridization, because VBT hybridization related, and in case of hybridization we won't consider any kind of pi bonding, that's why we won't consider this as a sigma bonding case, or in case of VBT when we are discussing the octahedral system. No problem. So now let me start let me explain the octahedral system from, in case of D system, okay, from basic to advanced, that means from D0 to D10 system. If you allow me to explain this, I will do that. Of course I will do that definitely. Some in between some cases I will be giving you some assignments, so do watch the video carefully, otherwise you can't solve the assignments, because those assignments you need to upload in the batch. Okay, so do not forget. Okay, D0 is about a complex. Let me take one complex like this, Al(H2O6) 3+. So it is aluminium 3+. You know the electronic configuration of aluminium: neon 3s2, 3p1, 3d is vacant, 3 is 0. Even you draw the 4s, that will be 0, 4p 0, 4d 0, everything is 0. You know that. Okay, and why is important? Why it is important? Very important. Why it is very important? Because if we consider aluminium 3+, that means these 3 electrons are not there. That means only neon. That means 3s orbital is vacant, 3s 0, 3p 0, 3d 0, and so on and so forth. So if I draw the orbital, that is I will be starting from 3d. Why is that? Because we will be considering only d orbital, because we are discussing the transition metal elements. So that's why I have started from D0 system, so that I can go from basic to advanced, D1, D2, like that. But in case of this, as we are considering the transition metals or d block elements, so we will be considering only d systems. Okay, because there are 6 ligands present over here. So ligand will interact with metal orbital. Okay, and metal has which orbital? Of course directly form sigma bond with which? With d orbital, and here the d orbital is 3d orbital, so it will interact with 3d orbital, 1 2 3 4, 3d orbital, and other orbitals are present like 3d, then 4s, then 4p, then even 4d. But we don't want to do any business with 4p 4d like that for this system. So there is how many electron in case of aluminium 3+? You just need to find out the oxidation state. How to do that? Aluminium has X, water is 0 charge, that means 0 equals to overall charge plus 3, X, that means aluminium has plus 3 charge, that is aluminium 3+. So that's how we can calculate the oxidation state that I taught you in the last video, EAN video, okay, effective atomic number video. So here there is no electron on the metal, or no electron on this 3d orbital, no electron in the 3d orbital. Even though as there is no electron over here, then also when 6 ligands are coming, they will directly they will form octahedron. As there are 6 ligands, they will form octahedron, and to form octahedron these kinds of rearrangement is important. And to find VBT, or to apply VBT, to find hybridization, we need to form sigma bond, and sigma bond is possible when direct interaction is possible. So in case of direct interaction, ligand must interact with the dx square minus y square and dz square orbital. So what are these 5 orbitals? X, y, y, z, z, x, x square minus y square and z square. So we need to consider only last 2 orbital. Listen, you can consider these 2, but for symmetry, because if you consider these 3, the x, y, y, z, z, x, like that, then it will be far more better, because you can use other orbitals also. But if you use these 2, then you have to keep these 3 vacant, because x, y, y, z, z, x. That's why just think that these are the last 2 orbitals. But otherwise, x, y, y, z, z, x, you can consider any of these you can consider. Okay, so I am considering that this is dx square minus y square, and this is dz square. Okay, so metal ligand will interact with metal only with these orbital. That means these orbital and these orbital, and these orbital are present. Of course, these orbitals are vacant for metal also, because I have shown you that 3d0, 4s0, 4p0, 4d0 all are vacant. So ligand can come and start doing interaction from d orbital to higher energy orbital. Okay, I think it is clear. So we will in this video, in this VBT video, we will mark metal electron like this. We will use this half arrow. Okay, arrow. And for ligand electron, for 2 electron, we will use this round sign. Okay, so 2 round sign means 2 electron, a pair of electron. And as a metal, the system should donate at least 2 electron. As a ligand, the system should donate 2 electron. So every time instead of like this, I will be marking the system like this. That means ligand is donating its 2 electron. To differentiate the ligand electron and metal electron, I am using 2 different signs. So first, there are how many ligands? 6 ligands. So 1 ligand will donate 2 electrons, 6 ligand will donate 12 electrons. So how to start? Where to start? We have to start from here. 1 ligand, 2 ligand, then 3 ligand, 4 ligand, 5 ligand, 6 ligand. Why I have started from that? Because these orbital x, y, y, z, z, x doesn't participate in this interaction, this sigma bonding, this hybridization. That's why you have to start from this and this orbital, and following to 4s and 4p orbital. And even in 4d orbital, it is also a d orbital, so it can interact like this way. Also 4d orbital should have these 2 interaction. Okay, first one and second one we can use only 2, because x square, one is x square minus y square, another is z square. So we can use 2d orbital from 4d, of course. Clear? So there is nothing like that. So 1, 2, 3, 4, 5, 6, we have used this 6 orbitals. So here we are getting what? Just look at carefully. We are getting this 2 like this. So there are 2d orbital, there are 3d orbital, that means it's 2d means d2, this is 1s, s, 3p, okay, 3p, that means p3, d2 sp3. This is called hybridization, and this is all about VBT. This is called hybridization. So for this system, for this octahedral system, you need to know the hybridization should be d2sp3. Okay, the hybridization should be d2sp3, and this hybridization will determine the structure as octahedral. This hybridization will determine the structure octahedral. If the system has this hybridization, if the metal complex has this hybridization, then you can say that the structure of the metal complex is octahedral. Clear? Okay, so I have discussed the D0 system. Let me talk about D1 system. Okay, but if you think that there may be one question over here, like, okay, so and the question will be like that, sir, you told that these 2 orbitals will participate into hybridization, right? But during hybridization, when you are fulfilling the electrons of ligand like this round ligand, you are using like this s orbital and p orbital. But how s and p orbital are participating in metal ligand sigma bonding? This question in your mind can arise. So let me tell you, you know about p orbital. How does it look like? Only this one, px, py, only this one, py, pz, only this one. Even you are considering s, spherical, this one. So you can see px touching to ligand, py touching to ligand, pz touching to ligand, even s, spherical, touching all the ligands. That means s and p orbitals are exactly doing the same what these two orbitals are doing, the d orbitals. So these two orbitals, d orbitals, dx square minus y square and dz square, and all the p orbitals and s orbitals will participate, will directly interact with ligand, form sigma bonds, and will participate into hybridization. That's why I am using 4s and 4p orbitals also. Why? Clear? Then if I suppose again we have something, we need to put extra electron like this, suppose, then which orbital is present? Again 4d, that is also a d orbital. We can take 2 orbital from here also. That is what is important. So here, as there is 2 electron present, we have to take, so this is d2 sp3 hybridization. I will be giving you some more interesting examples. Just keep watching the video. Another d1 system, Ti H2O whole 6 3 plus. So you know Ti is x, H2O 0, that means plus 3, x equals to plus 3, that is Ti is plus 3. Here Ti is plus 2 oxidation state, d1 system. As it is d1, that is 3d1, 4s0, 4p0, 4d0, everything. Clear? So if I draw the system like this, 3d, starting from 3d, because we don't, because before this there is a noble gas, argon, so we have nothing to do. Okay, argon, then 1 2 3 4 orbital, 5 orbital 1, p, and finally we need d, 1 2 3 4. No problem, we have got this. Now how to do this? So we have only d1, 1 electron, 3d1 for Ti3 plus. So we can put only 1 electron over here like this. But if I tell you that we have to put 6 ligands, 6 H2 ligands, that means 12 electron again, then again we have to use this trick. From here we have to start 5 and 6. So here what is this? This is 3d, this is 4s, this is 4p, this is 4d. So what is the hybridization over here? 2d, s, p, and 3p, 3, d2 sp3. Of course it will be octahedral again. Clear? Is it clear for d1 system? So similarly, if you can do for d2 system, it will be fine. If you can do d3 system, you can do this. So I am giving you homework for d2 and d3 system. Just do the same and try to find the hybridization and the whether the system, after finding the hybridization, just upload the video, upload the peak image in the benzene batch, corresponding benzene batch group. Okay, so that would be like d2 system and d3 system. So for d2 system, take vanadium H2 whole 6 3 plus, and take this like chromium NH3 whole 6, and finally it is 3 plus. So take these two and do the same thing whatever I have done, and just try that whether you are getting the same result or not. Okay, done. So I am taking d4. Why I am taking d4? That's the trick. I am taking d4. So our d4 example will be what? d4 example can be like chromium Cr H2 whole 6 2 plus, chromium H2 whole 6 2 plus. Another example I can take, that is Cr Cn whole 6, and that could be 4 minus. Okay, that could be 4 minus. Okay, now what should I do? Okay, I am taking 2 examples. Okay, just examples, nothing else. So this is a d4 system, this is also a d4 system. How to do that? So this is d4 means 3d4, 4s0, 4p0, 4d0. This is also true, 3d4, 4s0, 4p0, 4d0. Okay, so let me take the first one first. So if I draw the system like this, 1 2 3 4, 3d, 4s, 4p, 4d. Okay, no problem. let me put the electron. How many electrons? 4 electrons. 1, 2, 3, 4, according to whom's rule I am organizing the electrons. Okay, so here the question arises. Okay, I have put the 4 electrons of metal. Okay, these electrons are whom? This electron belongs to metal. These electrons belong to metal. Okay, here 6 ligands are present. So we have to find that which are the orbital that is going to interact with ligand. These are like, yeah, these 2 orbital, dx square minus y square and dz square. So find these 2 orbital in 3D. So one orbital is already, this one electron has captured. This orbital is captured by one electron, one metal electron. So how to use now? How can the ligand, okay, how the ligand can use these 2 orbitals now? Because ligand will say, no, I have 2 options. I will use these 2 orbital. Otherwise, I will not use any of these orbital. I don't want to use only these orbital. If the ligand use only one orbital, that means from in between this x square minus y square or z square, that means this ligand interaction will form or this will form. Both cannot be formed. Both cannot be formed, right? That's why ligand will say, I will take both of these one, otherwise I will not form the complex. But the system will say, no, you have to form the complex. So how could you do that? How should you do that? Ligand will say, yeah, in the system there are other ligand orbitals. So other metal orbitals, other metal d orbitals, where I can find dx square minus y square and dz square orbital vacant. Are you getting this? These two. These two or these two or these two, whatever you say, just two out of these 5, any 2. Okay, so I will be considering these 2 because these are close to this section. That's why I told you that if one orbital is present, then you can think, okay, there will be one ligand here. One ligand will be here. 1, 2, 3, 4, 5 and 6. DsP3D. DsP3D hybridization. DsP3D hybridization. That is not possible. Ligand cannot go into these 2 different d orbital. Either it will go into this or it will go into this. It cannot go half here. It cannot go half there. It can't do that. So to form the bonding, what ligand will do? Ligands will come and will say, no, as I have no place over here, I will start forming from here and use these 2 orbital. So 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So look at the system. 2, 4, 6, 2, 8, 10, 12. 1, 2, 3, 4, 5, 6. There are 6 ligands. What is the hybridization right now? sp3d2. What you got from previous one? d2sp3. Now sp3d2. So this belongs to octahedral. So there is slight difference. For the first case, in this case, for d1, d2 and d3, everything will be same. Okay. In this case, the hybridization is d2sp3. That means the system is using d inner one. The system is using only inner d. Okay. But in case of second one, the system is using outer d. You got the difference? In the first one, the system is using inner d, and the second one, system is using outer d. So what is the difference between inner d and outer d? So if you see that this is 3d, that means, and this is 4s, 3 and 4. This is n minus 1d. This is ns, this is np, and this is nd. So one is n minus 1d, which is called inner d, and nd, which is called outer d. Those can participate in metal ligand interaction. So this complex, that's why is called inner complex. Inner complex. Inner complex. And this complex is called sp3d2 outer complex. Why is that? Because this the second one is using outer d, 4d, nd, and the first one is using n minus 1d. That is the reason. That is the main reason. Clear? Okay. So I think it's done totally about the how the inner d and outer d and how the inner orbital complex and outer orbital complex. Actually, it is called inner orbital complex. Okay. Inner orbital complex, that is IOC, and this outer orbital complex, that is OOC. These are the 2 different systems. But if I take this system, I am discussing the d4 system. Okay, this I got outer orbital complex because there is no place for the ligand to go into this 3d orbital. But in case of this system, what I get, okay, let me draw the same thing in this next slide. Okay, here it is. So in this case, if I draw the same picture, then what I find, this is 3D, 4S, 4P, and this is 4D. Clear? So in these 3D orbital, what I get, 3D4, 1, 2, 3, and 4, and there is nothing like that. Okay, because it is a chromium 2+ system. So D4 system. This is the electronic configuration of this. Before this there is argon, noble gas, so we have nothing to do with that. We will just consider the d orbital because we are discussing the d orbital d block elements. Okay, so I told you that if there is all of the same, okay, these example show same result, so I shouldn't draw this, but there is something like exception, not exception, there is something like another thing. What is that? The thing is like this. In this case, what will happen? In this case, the fourth electron that should go over here, but it will not go over there. It will paired up with this first electron. It will paired up with this first electron. I have just drawn the arrow, half arrow, with a bigger size, so that you can get the idea. You can get to see, nothing else. Okay, you shouldn't draw this. Just draw the small structure. It will paired up with this system. So once it pairs up with this system, we will get two different orbital over here. One will be dx square minus y square, another will be dz square. Now 6 ligands can come and form a complex like that. D2sp3. This will be of course octahedral. So D2sp3 or sp3d2, both are same. Both will give the same structure, but the difference is inner and outer orbital complex. Difference is that. So what is it inner or outer? You can say of course inner, because it is using 3D, inner D, inner orbital complex IOC. So why this pairing is occurring, but this kind of pairing is not occurring in that complex? Why is that? Why is the reason? So there is some conditions. I will be coming to those conditions later on. Why? Because there are a lot of confusions in those conditions. Because let me tell you one line, because VBT theory cannot explain exactly the conditions. VBT theory cannot explain why this thing is happening exactly. VBT theory cannot explain this. That's why I am telling you that I will come to that later on after discussing the octahedral, square planar and tetrahedral section. Okay, and I will try to make you understand. Otherwise, and I will tell you when you will get to know that how these things is happening. Okay, I will tell you that one, and we will learn that in CFT, of course. Let me tell you right now. So without having any other thing, just let's move forward, and we are getting something. So here it will be outer complex, here it will be inner complex, and in those cases you have got that how we whenever necessary, the one electron will go from this orbital to this orbital to make available to inner 3D orbital whenever possible. Okay, so you just need to have the possibility. Okay, so you can get the idea about the system, that here it is chromium 2+, here it is chromium 2+. The basic difference is water and CN. So there is something with the ligand. Ligand should play some kind of role. What will be the role? That is important to know. That is very, very important to know. Okay, so you can get the idea that ligand will play some role, and because of that we will get sometimes outer orbital complex, sometimes we will get inner orbital complex, right? So do not waste more time. So let me come to the D5 system. D5. So in case of D5 system, I am not giving you example because it will be bored then. I will be just giving you example, but I won't discuss. 3D, 4S, 4P, 4D. 1, 2, 3, 4, 5. No possibility. That means in this case 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you will get sp3d2 outer orbital complex. Okay, but in some cases we will have this kind of facility. And what will be that? 1 2 3 4 5, and finally this one 1 2 3 4 5 6 7 8 9 10 11 12. So if I have here D2sp3, that will also give us inner orbital complex. Both will have octahedral structure, and it will also give you the octahedral structure. So if I give you the real example, the examples will be like that. For outer orbital complex, that means for the first one, I can give you the example like that. Fe H2O whole 6 3 plus. And for inner orbital complex, I can give you example like that. Fe Cn whole 6 4 minus. You can see here the same thing is happening. Here also the same thing is happening, and that is ligand. Here iron 3 plus, here also iron 3 plus, but here it is water, here it is Cn. That means there is something extra, something fun about the ligands. Ligand will play some kind of role, and what will be the role, that we will try to discuss after this video, after this VBT section, okay, today of course. And exact explanation we will discuss during CFT, crystal field theory. So at that time I will also give you the examples, and I will also give you again come back to VBT and make you understand why this thing is happening. Okay, done. Okay, so you can get the idea, and do one thing, just try to get that and take the structures and try to do this kind of thing. Okay, try to get the hybridization. Do not forget that these two and these two, you cannot use 3, you cannot use 3 from here. Okay, because the reason is direct interaction. I told you the reason. So taking D5 and taking, let me take D6, and you can, for the similar way, you can do D6. Okay, so I am telling you that which one will be outer orbital complex and which one will be inner orbital complex, and you have to do this homework and upload it into the benzene batch corresponding group. Okay, Hindi or English group, of course. For you it is English group. So the example will be like this: CO NH3 whole 6 3 plus, and another is Fe H2O whole 6 2 plus. So this is our inner orbital complex, IOC. This is OOC, outer orbital complex. Do one thing, do the VBT, do everything, find the hybridization, find the structure from hybridization, and just tell this is IOC, this is OOC, and do upload the picture in the corresponding English batch, benzene batch group. Okay, so this is your homework. Let me take D7 system. So it is very interesting, the D7 system. Okay, so let me take one example like that. So I told you, if I forgot, then I can tell you that this VBT theory, okay, this VBT theory, you know that this VBT theory is found by Pauling. Okay, I forgot. If I forgot, then let me tell you, because we have to give the credit to Mr. Pauling. Okay, so in case of D7 system, we can get the same thing. 1 2 3 4. Okay, done. 1 1 2 1 2 3 4. Okay, done. This is 3D, this is 4S 4P 4D. Okay, so D7 possibility, there are 2 possibilities. Let me draw another possibility like that. 1 2 3 4, like this. Draw with me. 1 2 3 4 5, and okay, done. 1 2 3 4 5 6 and 7. Clear. 1, we just need to get 2 vacant orbital. 1 2 3. We won't fill that. 4 5 6. Another electron is there. So I am putting over here right now. That means it will be present over here. So the 7th electron, where should I put? Where should I put the 7th electron? If I put the 7th electron, I cannot form inner orbital complex. Here it will be outer orbital complex. Okay, the ligand will be like this. This will get sp3 D2 hybridization, outer orbital complex, octahedral. Fine. In this case, where should I put the 7th electron? So Mr. Pauling told us, we don't know whether it is correct or wrong. According to whatever I am talking about, everything is about VBT theory. Everything is about VBT theory. So VBT, whatever the VBT theory is telling us, then I will be telling that one. Okay, I won't invent anything. I won't give you other information. So according to VBT theory, the founder of VBT theory, the inventor of VBT theory, Mr. Pauling, told that these electrons, to form the inner orbital complex, we have got already the outer orbital complex. So to form the inner orbital complex, we need to have these two orbital empty. So that's why this electron will be outside this section, and far away there is orbital like 5s. Okay, this is 3d, this is 4s, 4p, 4d, and then come to 5s. So far away there is an orbital they call 5s. This electron will go to this orbital, and to send this electron, the system said, because you are sending this electron from lower energy orbital to higher energy orbital, 3, 4, 5. If principal quantum number rises, then you get the energy higher, of course, for the orbital. Okay, so from lower energy orbital you are pushing the electron to higher energy orbital. That means you have to put some energy to the system to get this to make this transaction, to make this transition. Okay, so you have to add some energy, then, and the energy you have to add over here, it's very less. And what about very less? Should I compare? Can I compare with something? Yes, you can compare. Let me make you understand that. So now when this electron is going to there, then metal ligand bond forming will occur. That means inner orbital complex will form. How? Like this: 1, 2, 3, 4 ligand, 5th ligand, 6th ligand, 6 ligand. So 6 ligand will interact with metal. And why 6 ligands are interacting with metal? To become more stable system, to form more stable system. If I ask you why you are doing this, you will say because it is making me comfortable. Okay, it will feel you like you will be comfortable after doing this. So metal or ligand, they will form the corresponding bond, they will participate in bond formation when they will feel that after bond formation we will get the stability. Okay, so that's why this bond formation is occurring. So during bond formation, just get an idea about one thing. Have you ever seen the hot iron, very hot, red color hot iron? Just think. Or even kitchen, you can imagine this kind of situation. Just whatever I am telling, just try to imagine, try to visualize. If very hot iron, if you are putting it into cold water, okay, you will find that there is sound like shh, shh, shh. There is sound like that. Okay, and why? If you compare that sound, that the iron was hot, higher energetic iron, very high energy is there. When we are putting this iron into cold water, the system is relaxing. The system is trying to be more stable. The system is, the kinetic energy of each atom in the iron is getting lowered. Okay, that means the system is becoming stable. That means whenever it is getting whenever we are putting this into the water, it is releasing some amount of energy in terms of heat and gets colder, because it will be cooling, right? Once I put the hot iron into the cold water, it will be cold after some time. That means it is releasing its energy. So whenever metal and ligand, so can you just feel, okay, whenever metal, here is metal, a ligand is coming, different ligands are coming to the metal. So after bond formation, the bond formation will be stable. The complex should be much more stable. And to form a bond like that, whenever bond formation occurs, there should be some energy released from the system. You will find that some amount of energy will be released from the system. Clear? Like we are putting the hot iron into the water, there is heat energy is releasing from the system. So like that, you will be seeing that there, you can imagine that, you can feel that some amount of energy will release from the system once it gets relaxed, once metal and gets relaxed after bond formation. So this amount of energy the system will release, okay, but that means the stability energy, the stabilization energy, you can say it, the stabilization energy. To stabilize the system, the amount of energy system release, that is called stabilization energy. So the stabilization energy is this, and we have to transit this electron from this 3d to 5s orbital to make available these two orbitals to make inner orbital complex. And to do this, we need some amount of energy, I told you. So in this case, in this example, okay, in this example, whenever system is forming inner orbital complex, in this particular example, the system, what the system does, it needs less amount of energy to transit this electron from 3d to 5s orbital than the energy released by the system during bond formation. That means stabilization energy is more than this energy whichever you are applying to send this electron to 5s orbital. That means you are applying less energy to send this, and you are getting more stabilization energy, so the system will be stable. But if some kind of things is occurring, like when you are whatever amount of energy you are releasing, that means the stabilization energy, the energy is whichever is releasing after the bond formation, metal ligand bond formation, if the amount of stabilization energy is lower than the energy you are putting to send the electron to the 5s orbital, then the system will not obey this rule. The system will not send its electron to that, because you are not adding heat from outside like that. Okay, whenever you are getting that, just try to imagine that whenever metal ligand bond formation is occurring, what is happening, whatever energy metal during bond formation, whatever energy metal and ligand will release during bond formation, that amount of energy, from this energy, some amount of energy will accept this electron and go to this 5s orbital. Just try to imagine this factor. Okay, that the amount of energy that system will release from a small amount of energy, from that amount of energy will be accepted by this electron and go to the 5s orbital. Just think like that. That means if the stabilization energy is higher and this needed energy is lower, it is possible. But if the stabilization energy is lower, but to send the electron you need higher energy, then how would this stabilization energy can send the electron to this? That means in that case you can't send the electron to the far orbital. You can do the transition. So before going to that kind of example, let me give you some real life example for D7 system. So for this and for this also. So for the first case, for the first system, I am going to give you example like this. For the first one is inner orbital outer orbital complex, like COH2O whole 6, COH2 whole 6 2 plus, and another one is NiF6 3 minus. Done. So both are D7 system. This is also D7 system. This is also D7 system. So I hope you got that how these systems can be differentiated from inner and outer orbital complex. So this is called inner orbital complex, IOC, and this is called OOC. So both are octahedral. This is also octahedral. Clear? I think it's totally clear now. Okay, so we are done with that. So as I promised you that I will tell you that when the system cannot transit its electron to 5s. So for that, let me take another example like D8 system. So in case of D8 system, let me take one example, like real example, NH3 whole 6 2 plus. Another example like CuOH2 whole 6 2 plus. So this is a D8 system, this is a D8 system. Okay. Sorry, this is not a D8 system. This is not a D8 system. This is D9 system. It's become the D9 system. This is make this as like where is it D3 system. Make this as like copper 3 plus. So now it is like D8, yeah, both are D8 system. Just take hypothetically. So for the first system, the D8 system, that means this kind of orbital. Here also this is the there can be same possibility. So the first one, I want to form the first one. The first one will show outer orbital complex. Second one will show inner orbital complex. Okay, so that's how I am taking the example. So to form outer orbital complex, that means we have to use these orbitals. We have to use just these orbital. Okay, sp3. Okay, done. So for this D8 system, 1 2 3 4 5 6 7 and 8 D8 system, it's done. And here also D8 system. I am coming to this in the lateral one. So to just try to make the fulfillment 1 2 3 4 5 and 6. So there are 6 ligands over here, so I have already put the 6 ligands. So this is sp3 d2, 3d, 4s, 4p and 4d. This is sp3 d2, right? Same case if I do like this, so we want to form a inner orbital complex. That means we want to keep these orbitals, keep these 2 orbitals vacant or empty. So now what I need to do, 1 2 3 4 5 6 electrons we have done. So we have more 2 electrons like that. We need more electrons. We have more electrons, but those are different. 1 electron is like that, okay. If the system forms like this, then this kind of electron distribution should present in the system. So I am putting this electron. So to make available these two orbital dx square minus y square and dz square, we need to transit this electron to 5s. Again the rule is same. This is 5s, 4d, 4p, 4s. This is 3d. So let me do that one. If I am sending this, and I need to just pair up them. So if I do this, we need to put energy, and then metal ligand bond will form. So it is d2 sp3. Also this is called inner orbital complex, you know. Now the question is it really possible? Last time I told you that to send 1 electron, whatever stabilization energy it is getting, to send 1 electron, it has to provide a lot of energy to the electron to send it to the 5s orbital. Just think like that. But in the second case, whatever stabilization energy the system is getting after metal ligand bond formation, if you want to send the electron to 5s orbital from 3d orbital, you need to spend much more energy than whatever energy you are getting from the metal ligand bond formation. That means you have to invest more that your income. You are doing your income like 5,000 per month, and you are investing 10,000 per month. Then you will be in loss. Okay, so that kind of thing. So the system will not do that. And as the system will not do that, this kind of structure is not possible. In reality, is not possible. But according to VBT theory, it's possible. But I am cutting this because in reality there is no such examples. So according to VBT, it's possible, of course possible, because according to VBT it will send electron like that and do this kind of examples. But in reality, this kind of thing is not possible. So I hope you have got the exact information about the system, that which system will show which photon. So for D8, D9 and D10 system, it will show, I am not explaining now, D8, D9, D10 system, it will show what? Outer orbital complex. Outer orbital complex. Because here this kind of electronic configuration will be there. D9 and D10, then also it will be available. And one more thing that you should ask me, that sir, why I am doing that from this orbital or from this orbital, why I am sending it to 5s orbital? Because I have already vacant 4d orbital. From here, why I am sending the electron to 5s orbital? I have already vacant 4d orbital. I told you, you can't use in a system, I told you can't use these orbital as well as these orbital for a particular system. Either you have to use this or you have to use these two. You can't use both of these. So that's the reason. Even this is not for getting the same. Okay, this orbital is too larger than it will not accommodate this one, but s orbital will accommodate the same electron. Okay, so that's it. So it's the common question and it's normal. Done. Okay, yeah, got that. Okay, now yeah, we are done with the octahedral system. Now let me come to the square planar system. So how does it look like? The square planar system, you know, like this. Here is a metal, ligand 1, ligand 2, ligand 3 and ligand 4 connected to metal on a same plane, square planar, and this is our y-axis, this is our x-axis. There is nothing to do with z-axis. And if I talk about the interaction, you know that dx square minus y square, and there is no other orbital that will interact directly with the ligand. because you got that, of course, because there is nothing z axis. If it was z axis like octahedral, then of course it would be octahedral, it won't be square planar, but here it is square planar. Clear? So in this square planar system, the direct interaction is occurring with the dx square minus y square. So we need from the d orbital, we need only one orbital to form complexes. This is not that much famous, but I am showing you only one orbital. That means these 4 orbitals, the metal can use these 4 orbitals. Okay, so we need only one orbital. Okay, and we need 4 ligands, and that means 4 into 2, 8 electrons, of course. Okay, so that's all, that's done. It's very easy. And as I told you that along with that, s orbital generally, the nearest s orbital in case of transition metal elements, 3d, 4s, 4p, 4d, like that, this kind of situation generally occurs. So in case of 4s and 4p, they will also interact like that, because you know the s orbital is like spherical, p orbital will be, px will be like this, py will be like this. So px and py will also interact, but only take care of this thing, only px and py, only these two will interact with the ligand. Only px orbital and py orbital of metal will interact with the ligand, because you can, from the image you can see that this and this, x and y, not z, there is no z axis, so pz orbital will not interact with ligand. Okay, so one d orbital, one s orbital, two p orbital. So getting idea about the hybridization, one d s, 2p. dsp2 hybridization belongs to square planar. Are you getting fun? It's really amazing, right? So everything you are getting, whatever you knew till now, it's getting like interested. Okay, everything will be interested. Just wait for the CFT. It's quite interesting, the whole CFT. Okay, so now dsp2, that is square planar. You have already got the hybridization. So now let me give you one example. I will only give you one example, and I will give you one homework, because this is not that much famous. I just only give you one example, and whatever will be the example, just let me see, because I forgot generally real example. I just want to give you the real example. Okay, if I can if I give you any example, then I can do that, but I want to give you the real example. So for that I am taking like Ni, NH3 whole 4 2 plus. Let me take this example, just as a hypothetical. Let me take this example. Okay, otherwise I can give you AmL4 from very easy fact. Okay, so this is what, this is a D8 system, and the same thing will be true 3D, 4s, 4p and 4d, like that. So 8 electron. We just need what? We just need, there should be 2 possibilities over here. Okay, first possibility 1 2 3 4 5 6 7 8. So we have to start from this, like we have to start from this, like here, sp3. Okay, but it cannot happen. Why? Because I told you that for a square planar system there should be interaction with metal d orbital, because we are considering transition metals. The main interaction is with d orbital, so only one d orbital, dx square minus y square, will take part. That means here pz also take part, but that is not present in the square planar system. So whatever we are telling, that is about, we are doing something wrong over here. So let me correct this one. Okay, so the correct thing will be like this. One electron will be, there are 8 electrons. So in the previous case, one electron, there were total 8 electrons, but one electron will come here and it will paired up, and along with that, when it will paired up, that same reason there are some conditions to be paired up. The conditions I will be coming after the tetrahedral system, once we have covered all the octahedral, square planar and tetrahedral system. Okay, done. So another ligand electron pair will be coming over here. So now we are getting dsp2 hybridization. Now it's fine, clear. And it is what? Of course inner orbital complex, because we are using inner 3D. sometimes in some cases if you are using sp2 dehybridization, that will be outer orbital complex, but that is not that much famous, so I am not discussing that one. Just try to remember what is inner, what is outer. There is nothing else in that. Okay, no problem. Now we are done. So now what happens, I am giving you one assignment, homework, just do solve and upload on the group benzene batch. Okay, that I am going to example what, let me take platinum NH3, done. This, I hope you have got that. This is home task, or if I say this is your homework, this is your homework. Okay, don't take it as this is your hard work. Okay, don't take it, this is your homework. Okay, now its video has become 1 hour 11 minutes. Okay, now I have to finish this, but it will take a lot of time because we have to go into each and every layer. Okay, so that's why I am taking a lot of time to make you understand all the topics, all the parts. No problem. So we are done with the corresponding square planar system, but another system is left, that is tetrahedral system. And if you know already that tetrahedral system has sp3 hybridization, if you know already, otherwise forget this sp3 part. Okay, forget this sp3 part. So how sp3 hybridization is occurring generally? So you know that in case of tetrahedral system, the system looks like that. M 1 2 3 4, ligand 1, ligand 2, ligand 3, ligand 4, and each of these angle is 109 degree 28 minutes. So you cannot expect that this and this will be on x-axis, this will be on y-axis. You cannot expect this. You cannot expect this. Okay, because the angle is not 90 degree. If it was 90 degree, then you could expect that, yeah, the angle is 90 degree, so it will be, one will be on x-axis, another will be on y-axis. So the ligand, two ligands angle is 109 degree 28 minute. So how if I draw a system in a cube, then you will get to know that how the tetrahedral system, where the ligand is actually present in a system. So let me draw this first. Okay, so take a metal over here, and it is connected to a ligand like this, ligand 1. I am drawing the tetrahedral system. This second ligand will be crossed to this ligand along the crossing, okay, along the diagonal. Third will be like this, fourth will be like this, and this will also connected to this. This will be metal, this will connected to metal, everyone. And if you take from here, then you will get the first one, of course. So this is actually the first one, second one, third one, fourth one, and the central one is our metal. So this is our tetrahedral system. So if you draw the corresponding orbital over here, what would you get? What would you get? You would get like, this is x-axis, this is our x-axis, this would be our y-axis or z-axis, and this would be our y-axis, like that. So if you consider, then see, this will be our x square minus y square orbital. This will be z square orbital, like here, till here and till here. So in the corner, if you really imagine the structure, in the corner or through the corner, even you consider dx, y, y, z, zx, it won't touch the ligand. It will not touch the ligand. Never it will touch the ligand. Okay, so that's why no orbital is interacting to the, no d orbital. There is no d orbital which are interacting directly to this corresponding ligands in case of tetrahedral systems. So in general, that's why tetrahedral system, if I consider only s orbital, that can touch because that is spherical. For p orbital, that can come closer to these orbitals. Okay, so that's why we only consider that s and p orbital of a metal are participating in, okay, sorry, let me use another color, are participating in What? In hybridization. Hybridization, that is in VBT. Clear? Clear, right? Okay, done. So we are done with this sp3 system. So I am giving you only one example for this. Okay, so D1, I am taking D1 system. So I am taking the example TiCl4, titanium Cl4, and there is one minus. So this is the D1 system. How? X minus 4 equals to minus 1. So titanium 3 plus system it is, X value is plus 3. So titanium plus 3 is equals to D1 system. So look at this D1 system first. So in this D1 system, what you need to do? Need to draw the corresponding orbital 3D. So you just need to practice all those things. Then it will be very easy for you. 1, 2, 3, 4. So 3D, 4s, 4p, and 4d. What I need to? We just need to put 4 ligands. Look at this. 4 ligands means 4 into 2 electron. Total 8 electron. 1 ligand, 2 electron, like this. Okay. So here metal electron will be like how many? Only 1 electron. And you know that I told you only s and p orbital are participating on the in the hybridization. That's why you just need to consider this, and finally this. That will provide you sp3 hybridization. And I think you knew that the sp3 hybridization belongs to tetrahedral structure. Okay, so that is the main reason that in case of tetrahedral structure we are getting sp3 hybridization. The most interacting orbitals are that. The most interacting metal orbitals are that. Okay, so that's all. So here the inner d orbital or the outer d orbital never causes any kind of inner or outer like fact. So you won't find any IOC, you won't find any OOC for this system, for tetrahedral system. Only sp3 and sp3. So this is not that much famous. So do one thing, do calculate one example. Another, again I am giving you some hard work, and that is about one MnCl4 3 MnCl4 2 minus. Another one is to COCl4 2 minus. So do these two, solve these two and upload in the group. Okay. So that's all about this today's you know the which is this 3 different systems for VBT. We have discussed all one. Now we are talking about, let me talk about the conditions that I told you. So the condition, if I want to make you understand everything, I think I can't, but I will try definitely, because without CFT you cannot explain, because CFT will explain the exact reason the VBT won't explain. So we can just make you understand why this thing is happening. That sometimes we are getting inner orbital complex, sometimes we are getting outer orbital complex. So the condition, to explain the condition, let me open one example. D1 system. Okay, let me know D4 system. Yeah, D4 system. So now here you can see that here in this case, when H2O ligand is present, what happens? We are getting outer orbital complex. But when CN ligand is present, that means this, we are getting inner orbital complex. That means there is something with ligand, and how ligand causes this kind of outer and inner orbital complexes. That is our discussion fact. That is our matter of discussion. So there will be two fact. First is ligand factor. Second will be metal factor. So how ligand factor works? So there are some ligand, two types of ligand. One ligand which will have like carbon atom, phosphorus atom, arsenic atom, like that. These are electropositive system, and this system can easily donate electrons. Another is like F minus, oxygen O2 minus, like that system. So whenever these are all electropositive and these are all electronegative. Electropositive, electronegative. So when this kind of electronegative system comes, that means these are present in the ligand. Of course, we are discussing the ligand. When this kind of electronegative system which is present in the ligand and the charge of course on this system, then what happens? It has its own electronegativity. So it will attract its electron very close to its nucleus. So the system will be much more compact. But in this case, As those are not electronegative, so the system will be like diffused. Metal has its own electron. Okay, so we are discussing outer and inner orbital complex. Metal has its own electrons and its own orbital. Now let me go back to that point. This system. So we are first, let me discuss about the water. So here we are getting water and the whole system is neutral. This, listen, this system is not a electronegative system. Okay, this is water and this lone pair is donated by the system to coordinate bond. Okay, so this is not electronegative system, just do not consider that. I told you that exact explanation can be given through CFT, not from here, but I am trying. So here it is a ligand. Okay, consider this is a neutral ligand, so it is stable system already. So this system is more or less, it donates its electron easily. It can donate its electron easily. If the system is donating its electron easily, okay, then what happens generally? It cannot force the metal to redistribute this electron like this, as this ligand is very soft, this ligand is very weak. This ligand cannot force this metal to shift this electron to this, so that it can get to these two of these orbitals to make like D2sp3 hybridization. So in this system you can see there is an oxygen atom, that means the electronegative atom. So this is the electronegative atom, so it will attract its electron towards itself, it will not donate. Okay, because it is electronegative, it will say okay, it's my electron, I won't donate. So that is the reason that it doesn't donate its electron very efficiently. So it will keep its electron on itself. Now when it is not donating its electron, so ligand is a orbital, it's not donating, it's compact system, because it is not donating, it is attracting. So ligand, this metal orbital will say, yeah, I am not facing any kind of force. Ligand generally comes, they see that we don't have any possibility to get connected with this place, we are just coming and fulfill these orbitals to make the hybridization sp3d2, that is outer orbital complex, done. But in this case, you know that Cn is not Cn, Cn is actually Cn minus. So carbon has its negative charge. So carbon is electropositive element, so it can easily donate its negative charge. So when it will donate it, it will be very hopeful that someone take my electron, some metal will take my electron. So carbon will easily donate the electron to the metal, or carbon want to donate its electron. So that's why this system easily donate the electron, and it will donate. I will donate. Okay, metal, just do one thing. I don't want to listen to you. I just want to donate. I just take my electron. I just want to donate. Just take my electron. And at that point, what metal do? Metal will take the electron. How? This will take the electron in the d orbital, like this ligand is forcing the system to accept the electron. It looks like that this Cn ligand is forcing the system, 3D system, to accept the electron, and this electron will be redistributed or paired up to the first orbital like this, according to Hund's rule. Then here is two orbital available, so now we can form D2sp3 hybridization. So everything depends upon here. In these two examples, ligand factor is very important. Some ligand will donate electrons, some ligand will not donate electrons. Who donate and force the system to be paired up and make available the two orbitals, and some system will not, those are very electronegative elements, so those are very compact system, those are not easily forming any kind of thing. Another factor I can explain to you, that these ligands are not, these ligands are what? These ligands easily donate its electron. That means these ligands are diffused, not electronegative elements. So these ligands are diffused. Metal has its diffused d orbital, the ligand has its diffuse orbital, good interaction, good overlapping. So because of this good overlapping, d orbital and ligand orbital overlapping will be occurred over here. That's why d orbital will be available for ligand here. But here it is not donating its electron, so it is compact. So this is diffused, this is compact, not that much overlapping with this. So it will not give place for this H2 molecule. So it will be going to the outer orbital complex, going to form the outer orbital complex. I hope now it's cleared. If it is not cleared, I talk too fast over here right at this point. Just do one thing, just rewind the video or play it with 0.5x. Okay. So whatever, I hope you have got the point, that whatever I told you regarding ligand chemistry, ligand factor. Now let me come to the metal factor. Metal factor. So metal factor can be divided into two parts. First, there is metal present in first, second and third transition series. And metal, second factor is metal oxidation state. Simple thing, if metal has more charge, there are two systems, both system metal is present, but ligand is also same. In both system ligand is also same, ligands are also same, but the metal is it +2 oxidation state, it is +3 oxidation state. Now tell me, in case of +2 or +3 oxidation state, the interaction will be much more better, because ligand is negatively charged, it has electrons. Metal is the more the metal will be the positively charged, the more will be the interaction, more will be the attraction. So if more attraction, ligand will force more. If ligand is forcing more, the ligand d orbital will be organized easily, and we will get easily the inner orbital complex in case of higher oxidation state of metal, IOC. But here of course OOC, outer orbital complex, because metal is fixed, ligand is fixed. Okay, so here ligand is fixed, ligands are fixed, but metals are different. Metal is, suppose it is chromium, it is also chromium, but here it is chromium 3+, here it is chromium 2+. Now the problem will be with chromium 3+, ligand will attack and it will force the ligand, because it has more charge, more attraction will be there, and as more attraction is there, so it can easily form this complex. Let me show you, this will easily form this kind of complexes. More force, that means it will force the system to redistribute the electron, reorganize the electron, like to be paired up. Okay, because it is forcing, more oxidation state system will forcing the system, will force the metal orbital to get vacant, to get emptied. Okay, now here I hope you have got the point, that higher oxidation state metal will allow the system to form inner orbital complex, and lower oxidation state metal will allow the system to form outer orbital complex. So now we have another point to discuss, and the point is like metal we have discussed. Okay, metal present. So the simple thing, go to first transition series to second and third transition series, then you will find that whenever you are going to there, the size of the ligand, the size of the metal will be larger, and whenever the size of the metal will be larger, the d orbital size will also be larger. And for this reason what will happen, we will get that these metals is forming more inner orbital complex than these orbital. I mean, from if you go from top to bottom, then what we get, when you are going to the larger size of the metal, the larger size metal will form the inner orbital complex, because it has diffuse structure, so ligand will easily come and force itself. Ligand will come and overlap with itself with more efficient. Okay, efficiently it can overlap, and after overlapping it can force the metal to get in to form a inner orbital complex. Okay, so here it is. Finally we are done with that. So now let me talk about the magnetism property of complexes through VBT. So it is very simple. If a system, there is two types of magnetism. Okay, you know, the paramagnetism and diamagnetism. It is very simple. Okay, paramagnetism. So in case of paramagnetism, in a system, in a metal system, in a complex, you will find some half spin electrons. In case of diamagnetism, you won't find any half spin system. That means all the electrons will be paired up. But in case of paramagnetism, the system will be paramagnetic if in the complex you have some half spin electrons like that. But diamagnetism, in case of diamagnetism, you won't find that. You will find only paired up system. So do one thing. I am taking from the first, I just marking the system as paramagnetic or diamagnetic, P or D. Okay, let me take the first one. So here it is the first one. So in this case you are getting no electrons. So it will be, there is nothing like diamagnetic. There is no unpaired electron, that is diamagnetic. Here it is the unpaired electron. You can see here. You can see over here. Okay, so it is what? It is a paramagnetic system. The second one, it has 4 electrons. It is also paramagnetic. This one, for this case, it is also paramagnetic. It is also paramagnetic. Just look at this. Then coming to other system, like this is also paramagnetic. This is diamagnetic. Listen. Here there is no such as unpaired electron. Okay, this is diamagnetic. Now let me take this example, para. This will be dia. Yeah, this will be dia. If it is not possible, but according to VBT, this will be dia. Okay. Now, okay. In case of square planar system, this will be diamagnetic. Do one thing, I think that will also be diamagnetic. Okay, now coming to the tetrahedral system, this will be paramagnetic. So all paramagnetism and diamagnetism is based on this VBT theory, and it can be shown that this VBT theory is quite successful when it is talking about this, or it is discussing, or it is explaining the magnetism property of a system, magnetism property of a complex. That means whether a system is paramagnetic or diamagnetic, you can explain through this VBT theory. Okay, so now we are done with this VBT theory. Now let me talk about some limitations of this theory. Let me talk about some limitation of this theory. Limitation of this theory. So let me talk about those. First, I told you this VBT theory cannot explain the condition. Exactly. That means I told you that some electronegative, electropositive, say things like that. But there are a lot of exceptions. Okay, I didn't tell you, but there are a lot of exceptions that you cannot explain through electronegativity factor. So this theory cannot explain the corresponding condition, that in which condition inner orbital complex will be favored, in which condition outer orbital complex will be formed. Okay, that cannot explain. We will discuss the CFT theory, crystal field theory, can explain it very carefully, and also molecular orbital theory can explain it, but VBT theory cannot. Now another thing is VBT theory cannot explain the exact geometry of the system. So let me take two different example. Okay, that would be very interesting. NiCl4 2 minus, another is NiCN4 2 minus. So if let me just answer me. Okay, so here I have to take like this. Okay, done. 2 minus and 2 minus. So let me just give me one answer of one question. Can you tell, only seeing these two structures, can you tell that which will have tetrahedral structure and which will have square planar structure? If you don't know, I took the example because I knew that which one is tetrahedral and which one is square planar. But in this case, I know that this is tetrahedral and this is square planar. And this is true because I know. If you don't know, then can you do that from the VBT theory? You can't. So VBT theory cannot explain the exact geometry of the system. Okay, this is for some systems like that. Okay, you will have some problem. Because here also nickel 2 plus system, here also nickel 2 plus system. So both are same, just ligand is different. So with the different ligand, with the same coordination number 4, you cannot determine the exact geometry of the system. This is another. The third limitation of VBT is very important. That is, VBT theory cannot explain any color of the system. Why the color is blue, why copper sulfate is blue, why other system is green. VBT theory cannot explain this, the color of the system. Even VBT theory cannot explain the exact magnetic properties. I told you that the paramagnetism and diamagnetism property VBT theory, according to VBT theory, you can explain, but exact theory exact magnetic properties cannot be explained through VBT theory. Why is that? Because whatever we have seen right now, in general, for the first transition series, the VBT theory can explain. Why is that? Because in the first transition series only we consider spin angular momentum for the first transition series. Okay, but for the second and third transition series, there we should add another term, that is orbital motion, orbital angular momentum for second transition series or third transition series. That means for second and third, we are getting another term that is called spin orbit SO coupling. Okay, SO coupling. But from VBT theory, we cannot explain the spin orbit coupling like that things. We just only have the concept of spin, and if I get the spin concept, then we can tell that this is paramagnetic or this is diamagnetic through this concept. Okay, we will be talking about diamagnetism, paramagnetism, total magnetic behavior after the CFT. But don't think that I am ignoring paramagnetism and diamagnetism. We will be discussing in great detail. Okay, all these paramagnetic and diamagnetic properties. Now, as I told you that for the first transition series, VBT theory can explain, and VBT theory only explain the spin only value of magnetism. That means the magnetism which is which has been creating in the system through spin angular momentum. Okay, so if a system, if in a system spin orbit coupling, that means orbital angular momentum is present, and in most of the second and third transition series elements, those are present. In that case, VBT theory generally fails. It doesn't give the exact magnetism value, exact paramagnetism value. It doesn't give. That's the reason. Okay. So it cannot explain the magnetic properties right now. And finally, we can tell you that VBT theory has a very bad drawback. Okay, very bad drawback. That is about, there are some complexes like PT, let me write NHT whole 6, 2 plus. And finally, I am writing another example, Cu NHT whole 6, 2 plus. So if I take this kind of example, VBT theory will explain this, what will be the structure and what will be the corresponding hybridization. VBT theory can do that. But in reality, this complex does never form. These complexes never form. This complex never form. Okay, there is no existence of these kind of complexes. But VBT theory can explain the exact structure. So there is a system which is not present in the nature, but we can explain the VBT theory. We can explain through the VBT theory. So it looks like weird, right? So that's all about this VBT theory, and nothing like other things. A lot of other limitations are there, but those are not that much famous. And now we will be talking about some important topics. Like in the next video, I will be talking about the electro-neutrality principle, and then we will move forward to CFT. So from tomorrow onwards, we will be talking about CFT.